In this problem, we're sliding a box across the floor and we get it up to a certain speed and then we just let go of it. And so it has energy, it's moving, right? But from there, once we let go of it, the only thing acting on it is friction. So we know the mass of the box, we know its velocity, we know the coefficient of kinetic friction, and it's kinetic friction in this case because the box is moving. And the question is, how far will the box slide if you stop pushing it, right? So when we stop pushing it, that's the 0 point. We're going to measure how far, calculate how far it will slide from there. How do we do that? Well, let's start with, this is a conservation of energy problem. So the kinetic energy when you start off plus the potential energy, this is when you let go of the box. The kinetic energy when you let go of the box plus the potential energy when you let go of the box plus work done by non-conservative forces, in this case friction, equals the kinetic energy at the end when the box comes to a stop, plus the potential energy at the end when the box comes to a stop. Now, we have some things here that are going to make our lives a little easier right away, right? Mostly. What's the potential energy all along the way? Well, it's on the floor. So potential energy at the beginning and at the end is 0. At the end, it comes to a stop. And we know that kinetic energy is 1/2 mv squared. Well, when it comes to a stop, the velocity is 0. And because we know the velocity at the end is 0, we know that kinetic energy too is 0. So the kinetic energy at the end is 0, right? All we're left with is kinetic energy at the beginning. And I'm just going to go ahead and I'm going to edit this, put in kinetic energy 1 is 1/2 mv1 squared. Okay, we have kinetic energy and work from non-conservative forces. Well, the work from non-conservative forces is minus the force, in this case, it's the force of kinetic friction, times the distance that it slides through. And the force of kinetic friction is just mu k times the normal force, which is mu k mg, because the normal force is equal to the weight. So we now have the kinetic friction. We know how much that is. We now have an equation for KE1. So this term is this term and this term are the only ones that aren't 0. So let's write our simplified equation. 1/2 mv1 squared minus Fk, which is mu k mg. X is 0. Now we have an equation. The only thing in this equation that we do not know is x. Now, one thing you can see right now, the mass does not matter because I can divide through by the mass right now. I'm going to go ahead and do that. 1/2 v1 squared equals, I'm just taking the other piece to the other side, mu k g x. So I now have the equation getting close to where we solved it for x, right? I just have to divide by mu k and g, and I get x is 1/2 of v1 squared divided by mu k g. And we know everything in this equation. So we can go calculate it, and I'm just going to go over here and we're going to do that. v1 mu k g. So v1 is 1.47, pardon me, 1.47 meters per second, mu k 0.288, 9.81, and so x is going to be 0.5 times V1 squared divided by mu k times G. Now, you can see here what I've done is I've taken the denominator and put it in parentheses. Sometimes the easiest way to make sure you're doing the math right is to put the numerator in parentheses and the denominator in parentheses. That way you don't mess up and actually do things incorrectly. And here we go, 0.3933 meters. And it says state your answer in centimeters. Well, to convert from meters to centimeters, you just multiply by 100. So 39.33, that's a little over a meter. No, I mean, sorry, not a little over a meter. That's a little over a foot, right? So we have X is 39.33 centimeters. And that's it for this problem.